right, so this is an experiment in several ways. I've actually taught about the bomb quite a few times in my career because I think it's a very important topic. The threat to our civilization is real, and it is great, and people begin to forget. And I think teaching about the bomb is important to remind people what's out there and what its potential is. I put up here to start this letter, but that was just for the people who got here early. I want to see now if I can actually move on through my slides. And I'm going to start by pointing to three sources that I think are useful. And the major source for anybody who wants to know about how the atomic bomb came to be is Richard Rhodes's The Making of the Atomic Bomb. This is a superb book. He is an English major. He writes about the history, sort of the background, the culture, what finally led to such a weapon of mass destruction. He gets the history good, he gets the culture interesting, he gets the biographies of the participants, and he gets the physics right. He writes clearly and well. So I just think, you should all just turn off right now and go home and read the book. But we won't do that. The other thing which I think people should read is this is online. I think you could read it. Let me see if I can make this happen. Yeah, I was going to dazzle you all with my Zoom prowess by drawing on the screen, but we'll let that go for now. But I want to point out that this article by John Hersey appeared in the 1946 issue of the New Yorker. And you can surf online and find it and read it these days. It's relatively short, but it's poignant. It brings a kind of realism, a kind of reality to what actually happens when a nuclear weapon explodes over people. He traces the events, he traces the experiences of 6 survivors of Hiroshima, 6 people who were there when the bomb went off on August 6, 1945. And there were a lot of people who didn't survive. In fact, there were over 100,000 people who did not survive. We tend to lose track of what the human realities are when you have numbers like that. We think of the atomic bomb as a giant flash or a giant mushroom cloud, but that's, I think, really worth reading to understand what one is doing to people when you drop an atomic bomb. This third book is really kind of a plug for a friend of mine, Roger Stewart. But what it has in it that's different from all the others is an account of kind of what the life of a scientist was like who was trying to learn and do research in nuclear physics. In other words, the life, what he had to do to get some money. I mean, the money was, compared to today's standards, was a pittance. And so, and you had to go through a lot of hoops, you had to be kind of an apprentice to somebody, best of all if it was in Germany, because then that's where the physics was really good. But American physics was coming up. Anyway, he traces that. He calls this history of nuclear physics the age of innocence, because it's the nuclear physics before the bomb, before they make the bomb, when physicists were still arguably innocent. So the story, though, really starts in 1896. And it's really quite remarkable because you see here, I'm going to try my hand at drawing something once again. If you look at this picture here, you'll see that down here, there's a kind of a shadow of a cross. I don't know how many of you can see that, but you see there's this iron cross here. This is how Henri Becquerel first discovered radioactivity. He had a photographic plate that was wrapped in heavy black paper, but he had on it a piece of metal, or maybe inside he had a piece of metal in this cross shape, and he put uranium salts on the outside of the paper. I'm not going to go into why a person would do this, but he did it. He developed the photographic plate, and he could see blackening where the salts stood on the plate. And he could see that where he had this metal cross, there was no blackening. And what was going on? This was the discovery of radioactivity. This was the discovery that uranium salts were giving off some emanation, some kind of radioactive, what came to be called, what Marie Curie called radioactivity. Less than 50 years later, from the discovery of radioactivity to August 6, 1945, is a very short time in human history. And it's an amazing achievement. The physics is amazing. The working out of it through the 1920s, especially the 1930s. And then the Manhattan Project itself is an extraordinary achievement of collaboration of industry and scientists. And I'm going to try and do this in two parts. George Gamoda cleverly shifted this job onto me, and I do it willingly because, as I say, I like to talk about it. So thank you, George. And but he was right, and I was wrong about one thing. Was he was already going to do this in two stages, and I was saying, no, I'll do this in one stage, and then the next time I'll talk about the hydrogen bomb. I'm going to use both stages here, and I'm not going to take you all the way through the Manhattan Project today. I'm going to take you, I hope, up to the key moment when the Manhattan Project is begun, because there's just a lot of foreground, and also it's a chance for me to talk about some physics. Now, that's always a dangerous thing for me to do, but I'm going to do it anyway, so be warned. All right, so here we go. As I say, radioactivity is 1896. Ernest Rutherford is a key player in all this. He discovers what these radiations are that are coming out of the uranium salts. He doesn't know exactly what they are at first, so he calls them alpha and beta. You can tell they're different. The alphas don't go through much of anything. They're stopped by a piece of paper. The betas are quite penetrating. He discovers new elements, discovers radon. He discovers the law of radioactive decay. He discovers that there's this thing called a half-life, that these things all decay with a characteristic half-life. Uranium's half-life is 4.5 billion years. I forget what radon's half-life is, but it's minutes. He also finds the sort of energy being released by radium. I say energy content, but better to talk about it. He discovers radioactive transmutation of elements, and big for us, he discovers the atomic nucleus. He discovers that inside the atom is this very compact but extremely dense ball of matter that contains an electric charge, a positive charge. It's extremely dense. It's amazingly dense. I mean, it's quite bewilderingly, because it turns out that the nucleus contains roughly 99.99% of the matter. And it contains something like 1,000 trillionth of the volume. That's dense. I mean, when you put a little chunk of matter in such a tiny thing, and the density is a big deal. It's important to the story because it warns you that there's some very large force at work here that had been unknown until this time. This is great way to do physics, and we like to do it this way. You find that you can have protons, positively charged objects, extremely close together. We know they're extremely repulsive, but they don't come apart. Voila, we have discovered a new force. We call it the nuclear force. It's whatever can hold these things together against this enormously powerful electromagnetic force that's trying to drive them apart. And just to give you an idea of the kind of density here, I like this image. I worked it out all by myself. I'm proud of it. Here's the Nimitz supercarrier, about 100,000 tons. If you compress the Nimitz to nuclear density, you could put about 1,400 of them in a nickel. See? Nickel. 1,400 nimitzes. And I don't know if you can see it, but there's this kind of little blue spot right around here on the nickel. That's an image of a cube. Whoops. That's the image of a cube, about 3/4 of a millimeter on the side. You could put one compressed nimitz in that cube. Dense, very dense. Must be a very powerful force holding it together. Well, having the nucleus gave us our first clue as to what an atom structure was. And Niels Bohr is the person who looked at this. And so he's looking at hydrogen, and hydrogen is then, turns out to be a single proton with a single electron attached. So it's electrically neutral, negative electron, positive proton. He works out some of the atomic physics. He works out what kind of energies are involved with an electron around a nucleus. And they're in units that may not be familiar to you, so I want to talk about them a little bit because I'm going to use them throughout the talk. They're in units of we call electron volts. And an electron volt is a really tiny, tiny energy. It's the amount of work you have to do to take an electron from the positive terminal of a 1-volt battery to the negative terminal of a 1-volt battery. That's 1 electron volt. It's 10 to the minus 19th joules, joules being kind of like calories, but I don't want to worry about that. It's just that turns out to be a really convenient unit when you're talking about atoms, individual atoms and individual nuclei. And it turns out that atoms like the hydrogen atom, they have a kind of laddered energy structure. They can't, these are measured sort of from zero. And it turns out that if you attach an electron to a proton, you will get out 13.6 electron volts. Not a lot of energy, but you'll see. So 13.6 comes out. And so this is coming to the idea of what we call binding energy. And I want to talk about it because it's a useful idea. The idea is that an electron, when you put an electron on a proton, you get out energy. You get out 13.6. So if you want to unhitch an electron from a proton, you're going to need 13.6 electron volts. That's the binding energy. It's what it costs you in energy to take something apart. Well, this is my little picture of it. You have a proton, you have an electron, you put them together, you get a hydrogen atom, and you get out a photon, often written with the Greek letter gamma, and you get 13.6 electron volts. So that's what I just said to you before. Attach an electron, get 13.6. To break it off, it requires 13.6 electron volts. That's the binding energy. Now, what happens in chemistry is kind of interesting. And here's something that, because you say, 13 electron volts, not much. So here's even a smaller number. If you take a hydrogen molecule, and this is how you begin to do chemistry, or physicists like to do chemistry. I like to do chemistry. You take an oxygen molecule, 2 oxygens, but double bond. They are bound together. They have binding energies. The H2 molecule will cost you 4.5 eV to take it apart. The O2 molecule, 5.16 to take it apart. Now, if you take it apart and then reassemble it with 1 hydrogen on an oxygen and the other hydrogen on the oxygen, it turns out it will yield 4.87 eV for each of these bonds. Well, you do the arithmetic. You paid 4.5, let's see what I might want to say. Yeah, you have 2 hydrogen molecules and an oxygen molecule to make water. So you add together the binding energies, and then the binding energies when you reassemble them into 2 H2Os, and you find out there's some energy left over, which I call Q, and Q is 5.32 eV. 5 electron volts. You burn hydrogen into oxygen, you get 5 electron volts. Big news. Well, what does 5 electron volts mean? Here's what it can mean. This is the Hindenburg, a hydrogen-filled Zeppelin brought into Lakehurst, New Jersey in 1937. somebody was careless with their matches or something went wrong. It was a cosmic disaster, early times, but still it was filmed. And this all is coming from those 5 EVs, 5 electron volts per atom. So how come? This, when you work through, this will turn out to be, close to what you would get from detonating a ton of TNT. You're seeing there, except you're burning it. TNT is a little faster, and that's where you get your explosion from. This is just a heck of a big fire, which crumbles. Well, but that's what you can get from 5 EV. How come? Now, same thing happens that with this molecule, only a little differently. So in the hydrogen going to the oxygen, we were assembling the hydrogens with the oxygen to make water. And we were getting out energy because the bonds worked out that way. With trinitrotoluene, TNT, our kind of iconic explosive, you start and you take apart the bonds of the trinitrotoluene molecule. And you're going to get out, it turns out, about 10 electron volts, because when you take the things apart, you take apart this stuff, and then you assemble them into their components. These are more tightly bound than these things were. And you get a little extra, you get 10 EV. And that's where you get your explosion from 10 EV. But notice, in one case, we were putting stuff together and getting energy, and in this case, we're taking stuff apart and we're getting energy. It just depends on the breaks of the game, in a way. So, Steve and I wanted to experiment with you and with Zoom. And one of the things you can do with Zoom is you can poll. And so we're going to do a little poll right now, partly to assess if anybody knows what I'm talking about when I start using these exponential numbers, but mainly because we want to see if we can make Zoom do the things that Zoom says it can do. So we're going to take a few minutes. I've put up here 3 questions because Zoom is lousy for writing arithmetic, numbers or equations or anything like that. And Steve has put together our poll. So the first 2 questions have to do with, well, you'll see what they have to do with because they'll be on the poll. So I want you to see if you can read these things and answer the questions. Well, thank you for helping us go through this experiment. So here's our answers. So 50% of you say you know what Avogadro's number is about. 31% said you did once. That's good. So I would say, what is it? I don't know what the difference between red and blue lines is.
I think that's the majority answer.
I see. Well, really, really big is good. The only one in here that, I don't know about stick your arms out and measure it that way, but
now they can hear you.
The way I would read this is that this one is 10 to the 6, this one is 10 to the 12, this one is 10 to the 18, and this one is 10 to the 24. So these 3 are all smaller than Avogadro's number, which is 6 times 10 to the 23. And this one is bigger.
He's pointing to the different answers for number 2. Bigger than a million, 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 so forth.
Yeah.
Of course, Charlie, of course, everybody knows what a mole is, right?
Yeah. They're spies, aren't they? They live in your...
No, they're those crazy things that burrow in the ground.
Oh, okay.
Yeah, there's a lot of data in a mole, right? Or a lot of content.
All right, Mitch. I think
there's one in Burlington. It's the Burlington Mole.
Okay, yeah, then it's closed. All right, so we can close this and go on, I think. Very good. We're going to do one more test of our abilities to manipulate Zoom, and I'll tell you about that in a few minutes. All right, just in passing, this is a quick throwaway. Photons have an energy of about 2.5 electron volts. That's what this number is telling you here. The visible light, well, the visible photons have an energy of about 2.5 electron volts. And that's very interesting because you see, if they got much more energetic, if you went up into UV, you're getting towards about 5 electron volts. That's enough energy to start breaking chemical bonds. And that's why if you get in UV, you're going to start breaking the chemical bonds on your skin, which are fairly tough. And then if you go down below, you haven't got enough energy to do anything chemically all that interesting for our purposes. So you can see the sun is generating light that we're sensitive to, which is in a very nice range. Now, this stuff of photons and energy, that was actually first discovered or brought to our attention by Einstein. That's what he got the Nobel Prize for, really. He's explaining something called the photoelectric effect. And in order to explain the photoelectric effect, he had to show that light comes in packets of energy. Those little packets are visible light, are sort of 5 eV or a little less, a little more. No, between 1.9 eV and 3 eV is visible light. And he got a Nobel Prize for that. He didn't get a Nobel Prize for the special theory of relativity because when they gave him his Nobel Prize in 1921, they were still not sure he was right about the special theory of relativity. But key to us is the iconic equation. You know, if you ask people, say, do free association of physics and equations, what do you think of? Equal mc squared is the icon. And the point I want to make here is that I've made it already a couple times, is that all these little changes in energy are associated with a change in mass of the objects. The mass of an electron and a proton put together is a little bit less than the sum of the masses of a proton and an electron. The combination has a smaller mass by 13.6 electron volts divided by c squared. And that's what Einstein was telling us. Now, so this is, so I want to compare that energy with what's the energy coming out of the nucleus, because that's what's important to us. And it's an easy thing to measure. And it was measured already, you know, by about 1903, 1904, 5. It was measured before they understood Einstein's idea that it was equivalent to a kind of mass. You would look at it, say, what comes out of a radium atom, kind of thing that Madame Curie was looking at, and Rutherford was looking at. And what came out was this thing, the alpha particle, that Rutherford identified as a helium nucleus. And if you add up the mass of the radon atom and the mass of the helium atom, they are smaller than the mass of the thing from which they have come. They are smaller by an amount of mass which has an energy equivalence of 4.8 million electron volts, MeV, million. One nucleus of radium can release 4.8 million electron volts compared to one molecule of hydrogen, 3 eV, or one molecule of TNT, 10 eV. Millions. That's big news. And they understood it already in 1904. You see, this just builds on the idea a little bit more to point out that if you put together a proton, and protons are always red, and neutrons are, well, in this case, aquamarine. I'm probably violating standards. If you put together a neutron and a hydrogen atom, put it into the proton, they couple, and they make something which is still hydrogen, but it's got a neutron now with it. It's deuterium, we call it. It gets its own name. And you get off some energy. You get off millions of electron volts. The mass of this thing is less than the mass of these two things by 2.24 electron volts. If you could figure out a way to put these two things together, sorry guys, if you put these two things together, you get a helium nucleus, and you get 24 million electron volts. So this is big doings. And so I say people understood that in early times. Rutherford is said to have remarked in 1903 that some fool in a laboratory might blow up the universe unawares. I think we'd be aware of it when it happened. Frederick Soddy, another early researcher in radioactivity, says in a kind of much more elaborative way, the man who put his hand on the lever by which a parsimonious nature regulates so jealously the output of this store of energy would possess a weapon which he could by which he could destroy the earth if he chose. So look at the dates, 1903, 1904. People knew they had something, and they knew that it was potentially dangerous. Okay, now I want to spend a little time on this curve because it takes some talking about, but it summarizes pretty much what I've been telling you about nuclear energies and why you begin to look at it and say, oh my gosh, there's something really big time there. And so what's being plotted along here is the binding energy per nucleon. So that's a jargon term for either a neutron or a proton. And so a deuterium atom consists of 2 nucleons. A helium atom consists mostly of 4 nucleons, both of them. And that helium atom that we looked at, it had this a complete assembly. If you started with neutrons and protons and put them together, packed them in tightly, made a nice little ball, you got out 28 MeV. But there are 4 nucleons there. So what you're getting out is 7 MeV per nucleon, 28 divided by 4. And you see on the graph, this is about where mass number 4 is. That's your helium with 4 nucleons. That's the mass number of nucleons. And you see up here, that's right away halfway between 6 and 8. So 7 MeV per nucleon is what you're getting by putting together a helium atom or helium nucleus. You can't see it because it hardly shows, but if you take a neutron and a proton and put them together to make a deuterium, you're going to get out about 1 MeV per nucleon. You're going to get out 2 MeV total, but you'll get out 1 per nucleon. So that's what's being plotted here for all the chemicals that we know. We're plotting that. And you see, it's interesting. You go up, you keep getting more binding per nucleon all the way up to the top of the curve here. And the top of the curve occurs for iron 56. Iron has the most tightly bound per nucleon nucleus. We think that's kind of a reason why there's iron meteorites out there, that matter in the stellar universe tends to end up being iron because everything collides together. Well, I don't want to do that. But now here's what's interesting. You see, if we put light elements together, which I showed you on an earlier slide, we were getting out energy. This is telling you something interesting, that if you took something really heavy, say uranium, and you broke it into 2 fragments, so uranium-238, you could break it into 2 fragments, imagine, 119. It's more likely to be 2 fragments, one's 120 and the other's 118, but we don't have to worry about that. Anyway, you're going to break it into 2 things, which will come down to about here. And you see, this is a little more tightly bound than what's down here. There's a little, you're gaining some energy per nucleon when you do this. So look what's happening. Over here is what is getting energy from fusion. We think that's how the sun works. We think that the sun is taking light elements and combining them to make helium. And so you're bathing in the warmth of thermonuclear fusion. This, though, is a little different story. This is where the idea of fission becomes important, because it says if there was some way to cause a nucleus to break into 2 parts, you're going to get a little bit of energy per nucleon. I think the next slide actually shows the numbers a little better, so let's go to it. And yeah, this is the same curve, a little more, and with labels to tell you what's going on. So here's your uranium-235 on this curve, and it's being broken into something that says about 118. And so you're going to get this amount of energy per nucleon. Well, how much energy is that? Well, if you go over here and look, it's darn close to an MeV per nucleon. How many nucleons? You got 238 nucleons. You're going to get 238 MeV out of it. Well, say 200 MeV out of this thing, if you can get them to break apart. Masses of these things are very important. And that's my story. I mean, that's the main point I want to make. Now, at this point, I think Steve and this just summarizes what I just told you. Fusion, you put light things together, you get out energy. Fission, you break heavy things apart, you get out energy. And it all has to do with this business of binding. This is just like, when we put hydrogen and oxygen together, we made water, we got out energy. When we broke up TNT, we got out energy. So that's kind of cool. All right, so here's where I stop and I say, are there any questions? And if I'm a professor and I'm in a classroom, I wait approximately 4 seconds. I've actually watched professors at work and counted this with my pulse. You wait about 4 seconds and say, okay, then we'll go on. I thought it would be interesting to try using another feature of Zoom. So Steve has arranged to create breakout sessions. So we're going to put you in groups of 5 and ask you to talk to each other. We're going to give you 5 minutes, and we're asking each group to formulate 3 questions about what I've said, or anything that's on your mind about about the bomb project. Oh, and Mike Alexander adds a point that I missed. I should have mentioned, and that is that the Hersey article was also published as a book in every library in America, but you can get it online, which is just convenient.
It's a rather thin book. I read it in high school.
It's a
Probably
thin book.
more than 120 pages.
Yeah, that August 26th, it was the only article in the August 26th, 1946 New Yorker. They devoted the whole issue to his article. And so,
yeah, the book Hiroshima gave me nightmares for nights. I mean, it is horrendous what happens when you set off a nuke over a populated area.
why is Jerry Slate's asking, why is all matter not iron? Why are fission reactions not self-sustaining? Please explain again how photons participate. How are heavier elements made? Then he tells me the answer. Bob Primack, you're asking a question and telling me the answer.
Well, I'm asking.
First, only produce up to iron and then go to super.
Yeah, then what happens next? How do you get heavier? How do you get the heavier elements?
We think LIGO brought the answer to us about a few months ago, last year, in which you have neutron stars colliding and producing black hole and producing an effusion of heavier elements all the way up through gold. So we think that's
okay. Yeah, I think there was a recent article about that.
All right, so I'm going through here. The quantity of one molecule of deuterium, the energy consumed by one U.S. citizen in 1 year. No, it is not. Because it's only 2.2 MeV. So I think but maybe the question is that. All right, fusion, what's the state of art? That kind of takes me out of atomic bomb, but what happens to other products such as water? In your molecule equations, do you take into account the electron binding energy or just the differences between nuclei binding energies? In fact, the electrons are in there. If you use the kind of tables which are kind of ordinary thing for a nuclear physicist to have around, they are done with the electron binding energies included. But for most calculations, the electron binding energies are quite negligible compared to the millions of electron volts. Why are fusion reactors so hard to make? One answer to that, Jerry, is that they tend to melt their containers, and you have to contain them with something that is not material. You have to contain them with a magnetic field, and it turns out to be very, very difficult to make magnetic fields to do that, partly because the things that are inside them have electric charges, and they move around and they make their own magnetic fields, and the magnetic fields tend to create leaks in the containing magnetic field. And so that's the real issue. Why is all matter not iron? I don't really, in a way, Jerry, I don't know the answer to that. You know, an answer is that, you know, you do make the elements in stars which have not gone to this equilibrium state. And that's kind of evasive, but I would have to think more about
Oh,
it.
remember how am I on?
Yeah.
Jerry, is that you? Yeah?
Lee Grossman?
Oh, Lee, yeah.
Yeah. Well, remember how the periodic chart is made. It's made via fusion up until you reach iron. And after that, it's made by neutron capture
Yeah.
and beta decay. As the neutrons capture into iron, the beta decays, you go up one. And then that gets, and if you have enough neutrons around, which
I don't think that quite answers the question. I think what's happening is you're going up that chart, and locally adding a neutron can take you to something which is a little lower, a little more tightly bound than something that is a little bit lower down the chart. It's kind of like going up a staircase. I would have to.
yeah, no, that's right. That's right. The most stable one is iron 56, but if you flood the nucleus fast enough with enough neutrons, then iron 56 will capture neutrons, go to iron 57, that'll capture iron 58, etc., and those all then decay to higher proton numbers.
Right. So if you were to look, you know, I showed you the binding energy curve.
Yes.
And it's unduly smoothed out. If you look really closely, it has kind of little jig jags in it, and you can sort of maneuver over one little tiny peak into a little tiny valley, and you can keep going up that line without the thing coming apart. But what we want to do now, I think, is get back to the question of how we are going to put all this stuff, these facts together to make a weapon. How did people come to realize you could do that? And so I want to tell you, I really haven't got a lot more time. I got a half an hour left today, so I want to get back to that.
Yeah.
So I don't know, Steve, can we copy and keep this list of questions that's in the
Yeah,
chat?
don't exit when you're done, and I'll talk to you about it.
Okay, great.
Don't leave the meeting at the end.
All right. So I think I'm going to go back to sharing my screen if I can. And here we go. Share. All right. So I don't know. Now I've lost. So all this business, I wanted to add a little point here. All this business about masses and energy means that knowing the mass accurately, precisely, is quite important to understanding what nuclei are going to do. And one of the earliest people to create accurate measurements of the mass was Francis William Astin. He got a Nobel Prize in chemistry. He really took some ideas that were around and invented out from those ideas the mass spectrograph. And the mass spectrograph, turns out, is important for making nuclear bomb. And the idea is very simple. Here it's shown schematically. There's an ion source. There's a source where you put out atoms that have had a charge or two charges removed. You send them through a potential difference. If they're electrically charged, if they're positively charged ions, then they're repelled by the positive plate. They're attracted by the negative plate. They gain energy, and they come out on this side of the plate with a velocity. You then put them through a magnetic field, and so this schematic is showing a horseshoe magnet here, and there are green magnetic field lines going from one pole to the other. And the electrically charged particles will bend on their trajectory as they go through the magnetic field and then go in a straight line over and hit a target, might be a photographic plate. And so you could measure how much they are displaced. And from that displacement, you can actually, and some other things, you can figure out what the mass is of the ion. And you can do this with ever increasing precision and with better and better instruments and some new kinds of instruments that I'm not going to talk about. We can now measure these things to 9 significant figures, extraordinarily precise. But Astin was the first. He got a Nobel Prize for it. Here is a picture, I think, of his apparatus from a museum. It's this same apparatus here, but rotated now so that you're looking from the ion source through there's a gap between this part of the magnet and that part of the magnet. And I'm telling you this in part because I want to emphasize again that knowing the masses is important, but also because this device is going to turn out to be very important later in making an atomic bomb. But again, just repeat myself, measuring masses enables you to predict the energy that might be released. So for example, here's uranium-238. It decays by emitting an alpha particle, a helium nucleus. It's going to take out 2 charges. So uranium has 92 charges. So it's going to create an atomic element that has 90 charges, and that's thorium. And then it's going to take out 2 neutrons and 2 protons together. So the mass number is going to change by 4. So it's going to be thorium-234. You can look at the mass of uranium-238. You can look it up in a table. This is in atomic mass units. You can look up, you can actually look it up as 238 plus the energy equivalent of 0.0579, 47 MeV. You can do this for the alpha particle. You can do this for the thorium. You can add these things up, and you find out that there's a decrease in the amount of mass between thorium, alpha, and uranium of this tiny amount of mass units, which is 4.27 MeV. And that's the energy of the alpha particle, most of it. Point is, breakup can yield energy. We said that before, it's again. Now, you get that from knowing the masses. Now, you know that, but by 1930s, anybody who's looking for a source of power in the nuclear transformation of atoms was talking moonshine, says Rutherford. This is the same Rutherford who said 30 years earlier that some idiot might blow up the world with atoms. Now he's saying, oh, forget it. And Niels Bohr, talking about various effects of radioactivity and radioactive decay and nuclear transmutation, changing one nucleus into another, says these effects scarcely bring us nearer to the solution of the much discussed problem of releasing nuclear energy for practical purposes. Indeed, the more our knowledge of nuclear reactions advances, the remoter this goal seems to become. Well, this is 1936. So what's happened? What's the big change? And here it is. In 1932, Chadwick discovers the neutron. And I say here, for short form, it makes everything clear. Suddenly, you can understand a whole lot of things that you could not understand before. And one of the things you couldn't understand before is the fact that almost all nuclei have masses which are twice the number of their protons. Give or take a little bit, but that's pretty much the rule. So Rutherford said, maybe you have twice as many protons in the nucleus as you think, and then you have half of them canceled by electrons that are there, so that somehow there are these electrons neutralizing half the protons, and you end up with the atomic number of protons as the charge of the nucleus. That, he thought, was a perfectly reasonable explanation. Werner Heisenberg discovers quantum mechanics 1925, 6, 7, it's worked out. And he shows quantum mechanics absolutely forbids that there should be electrons localized in a nucleus. You cannot have them be in such a small volume without them having enormous energies which would enable them to escape that volume. So they can't be there. However, Chadwick discovers the neutron, and immediately Heisenberg points out a nucleus as an assembly of neutrons and protons, that's okay. That is consistent with quantum mechanics. And now we have the model of the nucleus, which I think most of us know is quite simple. It is a ball of neutrons and protons. You see, I told you that protons are blue, but I always thought, I'm sorry, that neutrons are blue, but I always thought protons were red. So, you know, these guys got it wrong. Anyway, that completes kind of our, all we need to know about the nucleus to get to create a bomb. And this notation I just want to review for you because I've been using it and I'll use it some more. You can write a chemical element, any chemical element X, by its symbol. Here's hydrogen, here's uranium. You can write the mass number of that nucleus. So for hydrogen, it's 1, and its charge number is 1. And you can write its neutron number as 0. There is hydrogen that has 1 proton and 1 neutron, and so it has a mass number of 2. And that's what we call deuterium. There's even tritium, which has a mass number of 3 and 1 proton and 2 neutrons. Each such an entity is called a nuclide. We don't have to worry about that. Here's uranium. Uranium has 238 nucleons, has 92 protons, it has 146 neutrons. Now, this is actually redundant information. If you're in the business, people say you're supposed to know uranium has 92, so you don't even write the 92. And if you know it's 92, then you know that the number of neutrons has to be the mass number less 92, 146. They don't write that either. So you'll just see people write U-238, and you're supposed to be able to figure out the rest. Uranium-235, same charge, that's what makes it uranium, but fewer neutrons. Odd number of neutrons turns out to be crucial. And who knew that this was crucial? Several people. Leo Szilard is one of the instigators, one of the really big name creators, big, what do I say, big, he had a gift of foresight, which was unusual. Once the neutron was discovered in about 1934, Rhodes describes Szilard stepping off a curb somewhere and suddenly realizing the idea of a chain reaction being possible. I think you all understand the idea of a chain reaction. What was not feasible until 1938, what nature enabled nature to be parsimonious about releasing the issue, the energy, is that there was nothing that would penetrate a nucleus and stir it up until the neutron was discovered. And then people realized neutrons can be wonderful probes because they're not electrically repelled. They can go right into a nucleus. If you want to put a proton into an existing nucleus, you need an accelerator that will bring it up to a very high energy. He realized that there's a possibility that you might cause some kind of radioactivity by a neutron coming in, and that radioactivity might spread to adjacent atoms in the sample and then spread further and further, and he had this idea of a chain reaction. It was a little fuzzy in his mind, was sufficiently clear in his mind that he got a patent on it. He patented it. He was also very sensitive to the need for secrecy about the possibility of nuclear weapons. And so he worked around and found a way to patent his idea of chain reaction secretly by patenting it with the British Admiralty. I think kind of catches his secrecy. He is talking here to Ernest Lawrence, who was the inventor of the cyclotron, the first really effective high energy accelerator of protons. One of the things you could do with an accelerator, if you could make protons go fast, is you could make neutrons come out of the reaction. And then you can use those neutrons for stuff. Lawrence was a very forceful figure and a gifted fundraiser and a machine man. He wanted ever bigger machines, and he raised money in quantities which seemed staggeringly large to the physicists of the Depression 1930s. And when he wanted something, he went after it very hard. And Szilard is here talking to Lawrence. I don't know, catching him with his finger on his lips. You might think he's talking about secrecy. But he and Lawrence both are very important people. And the idea is that finally breaks loose the possibility is nuclear fission, a possibility of making a nuclear weapon is fission. That occurs when you add a neutron to a uranium nucleus. And it turns out the energy of the neutron that you add doesn't have to be very large. In fact, it can be as low as a few 40ths of an EV, say 1 electron volt. None of this MeV stuff. If you put a 1 EV electron into a uranium-235 nucleus, that nucleus is going to come apart. It's going to break into 2 pieces. So Frisch is saying, that's impossible. And I thought I'd put this up because the irony is that a few years later, after he says this, or maybe he's saying this at the time, he's realizing he and his aunt, Lisa Meitner, who was really the person who understood what was going on, they are recognizing the possibility of nuclear fission. I'll tell you a little more about the story in a while. And Frisch goes home to Copenhagen, to Niels Bohr's lab where he's working, asks the biologist, gee, what do you call it when a cell breaks in two? Oh, and the biologist says, you call that fission. And so Frisch attaches the name of fission to nuclei. And that's our progress. That's where it comes from. And so this is the idea, this is the idea that establishes the possibility. Well, I think it's a nice story, and maybe I'll just tell it short form because I can't resist a good story. As soon as the neutron was discovered, so that's say 1932, 1933, Fermi in Italy realizes it's a wonderful probe, that you can stuff it into nuclei with great ease. And he does this. And he immediately discovers he's making new nuclei because sometimes the neutron will stay in the nucleus. And then the nucleus will be made radioactive by the presence of the neutron and will change into a different element. And he was doing this with lighter elements, but he also was doing it with heavy elements. And he was saying, I'm adding I'm adding neutrons to uranium nuclei, and I'm getting new chemically different species coming out. And so it must be making transuranics. And he was making transuranics. In 1933, he didn't realize it, but he was also causing nuclei to break in half. You remember, if a nucleus breaks in half, out comes 200 MeV. The irony is that it still took another 6 years before anybody understood this, and fission was not discovered until 1938, 39. And it was Otto Hahn, a nuclear chemist, who, studying the fragments of nuclear energy, of nuclei bombarded by neutrons, said, there's barium in this stuff. And everybody's saying no. And he was saying, no, it can't be barium because barium is roughly half of a uranium nucleus. It can't be barium. And he agonized over this for many months, did extremely careful chemistry, repeated his experiments, and concluded finally, it's barium. I have to tell the world it's barium. He wrote a letter to Nature saying, I have discovered barium in these, when you bombard neutrons. He also had worked closely with Lisa Meitner until she had to flee Germany to avoid Nazi persecution. And she was in Sweden, and he was writing her regularly. and telling her about its barium. So one winter day, Lisa Meitner and her nephew, Otto Frisch, went out for a walk in the snow and sat down on a log, and she told Frisch that Hahn had sent her a letter saying it's barium. And as they sat on the log, she said, you know, I see how the energies could work out. And I see how a picture that Bohr has of how a nucleus can be kind of like an oscillating drop. I can see how, you know, the energy might, adding a neutron to this might cause the droplet to break up, sort of go out to a neck, sort of into two droplets with a neck between them. And then the nuclear force would be weak between the two, and the electric force between the two would still be enormous, and they would fly apart. And out would come. And she's sitting on the log, actually knew the masses well enough to figure out, you know, oh my goodness, 200 MeV might come out. And so that's the story. That's the story of breaking into fission. And that's a key step, because now you see that there is a source of energy. Now the question is, there are a lot of questions. First of all, they didn't know what the neutron was interacting with in uranium. I'll explain that in a minute. They also didn't know what came out with the fission fragments. If you want to have a chain reaction, you got to have more neutrons come out. Like this is showing, and this is showing 3 neutrons coming out, and 2 of the neutrons are going on to hit other uranium, in this case 235, and now you're going to get a multiplication. Now you're going to get a chain reaction. Now it gets really interesting. The early calculations of this were not as interesting, partly because the early calculations said in order to get a bomb, you'd need to have 13 tons of uranium. Well, actually, the first numbers I think were like 100 tons or 30 tons, and then they got narrowed down to 10 tons of uranium. However, people were starting to think about this. Szilard, shown here looking somewhat older because this is reenacted after the war, says there is a possibility of a weapon. We must tell the authorities. And he's a very cagey man, politically sensitive. So he says, we need somebody who is famous to sign the letter so that the president will read it. And so he goes to Einstein, he drafts the letter, takes it to Einstein. The letter says, watch out. Uranium turns out to be of possible military importance. The Germans know this. They've already stopped exports of uranium ores from their mines in now conquered Czechoslovakia. And America should get on the alert. And he writes this letter. Einstein signs it. They send it to FDR, President Roosevelt, through a mutual acquaintance, somebody who was a friend of Roosevelt's and somebody who Szilard knew, a financier named Sachs. They send a letter warning, and you notice that if you notice the date on the letter, it's August 1939. All right. I should stop and see if anybody's got any questions at the minute. I should stop and see if I can find my own video because I've lost video contact with you all. There we are.
We see you. You look a little perplexed, but we do see you.
Okay. I've been lecturing, you know, with essentially a blank screen for the audience. I could see my slides all right, and I was beginning to get worried.
We're looking at you, Charlie. We can see you talking.
All right, good. But I'm going on and begin to feel like you're talking to yourself if you don't see some other faces. So,
I noticed that when I gave a lecture. It's funny talking to a screen.
Yeah, right. All right. So I've done all right there, but now I've lost my pictures of my slides. I'm Zoomless. Let me see if I can get them back. Oh, sharing is paused. All right, I'm good. Okay, I'm good. I'm back. Now I actually see you guys as well. That's nice. So, what's going to happen? You see, we're coming up to a kind of crucial point. It's probably where I should stop. But we now know that there's fission. It's 1939, it's fission. The message comes immediately around the world. And I want you to understand, everybody understood right away what fission meant. The Japanese understood it, the Germans understood it, the Russians understood it, the British understood it, and now the Americans understand it. They all understood that if you have fission, and if fission can produce a few extra neutrons, each fission produce a few extra neutrons, then you've got something very serious, serious possibilities. Each country, each of those countries sets up a committee to investigate the possibilities of the energy extraction from uranium. We are absolutely not alone in that. We said this letter causes Roosevelt to set up a committee headed by a guy who's been director of the NBS, National Bureau of Science, Simon Briggs, and he collects a few people knowledgeable about it, and they are to make recommendations. Now, there are other things going on that are crucial to the setting up of the Manhattan Project, and so I'm gonna skip the physics for a while, to be all concerned, right? And talk a little bit about key personnel. First of all, in science, Vannevar Bush is an engineer at MIT. He has had an experience building stuff, doing scientific research for weapons for World War I, in which he said they produced good things and they never got used because the Army bureaucracy was so bad. And he says, in 1939, on his own, he says, I'm going to go to Washington and I'm going to prepare for this war, which we all think is coming. And it's even before the war has begun in Europe. He says, I'm going to go to Europe. He takes on the presidency or the directorship of the Carnegie Institute, which is a research institute based in Washington. The president of MIT doesn't want him to leave and says, look, if you won't leave, I will move up to the board of trustees and you can become president. He says, no, that's not what needs to be done right now. I'm going to Washington. I want to be in the Washington area where I can lobby effectively for a decent organization of scientists to prepare weapons for the war. So he goes to Washington. He's head of the Carnegie. That's kind of his civilian job. But he's talking to other scientists. He's gathering them together. And in June of 1940, using Harry Hopkins, Roosevelt's principal advisor, Bush sends him a memo saying we should establish something which I propose to call the National Defense Research Council. June of 1940. By now the war has started in Europe, but it hasn't started here. And Roosevelt buys the idea. And so there is now this thing called the NDRC, and it's recruiting physicists to work on urgent technical problems. The first thing they work on is a proximity fuse, something that will make a artillery shell go off when it gets near its target rather than having to strike the target. Better for anti-aircraft, obviously. And he's gathering scientists together and getting to do that. Things continue to evolve, and I'm going to skip the details of the evolution, but by June of 41, for reasons that I will talk about in a minute, the whole business of scientists working for a war that's coming has reached a serious level where he wants serious amounts of money committed to. He wants an organization that reports directly to the president. And so the NDRC, I guess it still exists, but he gets created something called the Office of Scientific Research Development, OSRD. This is the body that is going to lead to the creation of the Manhattan Project. And he recruits into it kind of the major scientific leaders of America. Roosevelt, as I say, buys the idea. A key figure in getting this idea sold is Arthur Holly Compton, a he happens to be the brother, well, he's a Nobel Prize winner in physics. He's also the brother of the president of MIT, who was at that time was Carl Compton. And he leads a committee from the National Academy of Sciences to review the work of the Uranium Committee that Roosevelt had created in response to the letter from Einstein. And not much has happened. So here I am, 2 minutes in the end. Where things were really happening was in England, because there, Piles and Frisch, the same Frisch who said fission couldn't work, and then said, oh my God, it works, has come to England. They're both refugees. They are the ones, the first ones who realized, no, if you used pure U-235, which might be obtainable, your bomb is not going to be 10 tons. It might be 10 kilograms. It might be something the size of a grapefruit. This is a whole different picture. And it's very persuasive to the British. It's so persuasive that when they write a memorandum about it and send it through their boss, Oliphant, they're in the physics department, he said, yeah. They're enemy aliens because they're both German refugees, and Britain is now thoroughly at war with the British. So their memorandum is classified and they may not read it. So there you go, the beginning of security and the problems. So they have to quickly make them British citizens so they can read their memorandum again. And this happens. Anyway, it goes to Oliphant. Oliphant takes it to the British, and the British say, this is really serious. You could really make a bomb. What's going on in America? James Conant, who is working, he's currently the president, at that time he's president of Harvard, and is now working closely with Bush in OSRD. He comes to England. They tell him there's something going on. I want to skip that for a minute because finally, the British say, why aren't the Americans doing anything? And they get in touch with Lawrence and persuade him that this weapon is really possible. Lawrence goes kind of ballistic and goes after Bush. Here are the science leaders. This is Lawrence sitting here. This is Arthur Compton. This is Bush. This is Conant. This is Carl Compton, the president of MIT. So you have the president of MIT, the president of Harvard. You have this guy who comes out of MIT and goes to Washington and sets the thing up. You have this guy who's coming from the National Academy of Sciences to review the ideas that are being brought forward and pushed very hard by this guy. This is Alfred Loomis, who is the last private, he's a millionaire who does science as a hobby and has a fancy laboratory up in Tuxedo Park, New York. Anyway, he's involved with these guys. Helps fund some of them. So these guys are persuading Bush that something's got to be done. And I'm going to skip this quickly to say only that by this time, people understand, thanks to a summer study from Berkeley run by J. Robert Oppenheimer, that there is the possibility of a bomb. Not only one way to get a bomb, there might even be two ways. You might be able to separate out the uranium-235, make it pure enough so that it will make a chain reaction, or you might be able to use uranium-238 and bombard it in a nuclear reactor, which nobody has made yet, and make plutonium, which itself would be fissile, and you can make a bomb out of that plutonium. Two paths to a bomb. What's crucial? Two paths to a bomb. Two ways to do it. And now comes the big decision. And this is, to my mind, one of the key figures of the whole thing. Much disliked by physicists, often belittled by physicists. He is Major General Leslie Groves. The Army, Bush says to make anything happen, we're going to have to involve the Army because there are going to be some huge construction projects. Only the Army is capable of doing these huge construction projects. We need someone who can lead such an event, do it with real force. And he turns to the Army, and the Army says, oh, we know the guy. He's just finished building the Pentagon. He's just finished doing a multi-billion-dollar project under budget and in less than scheduled time. He's your guy. He is the guy. He's appointed. As I say, the physicists never liked him very well, but he makes an amazing number of decisions. He's replacing a guy because the Army had gotten involved in June of 1941. The Army had been brought into the development. He replaces this guy who had his office in Manhattan. Had an office, so a guy he was a Colonel Marshall, not the Marshal who was chief of staff, but a different colonel, different Marshal. And he had his office in Manhattan. And the way he covered up his involvement with a secret bomb project was to call it the Manhattan Engineering District, named there for where he had his office. So Groves is replacing this man. And now we have the creation of the Manhattan Engineering. The district has already been created in a way, it's named. But now we put in charge of it a man who has enormous force of character, an extraordinary capability of making decisions. The day he's appointed, he runs off and buys 52,000 acres in Tennessee for a uranium separation plant. This is the kind of rapidity with which he's going to work. More about him next time. But this is the place where I think I should stop. We've gotten through the physics, and it's now time to see how to make the physics turn into a real one.
I wanted to tell you about Werner Heisenberg. He was once driving along too fast, and a policeman stopped him for speeding, and cop saunters over to the window and says, "Do you know how fast you were going?" And Heisenberg looks at him and says, "No, but I knew where I was."
The first time I heard a Heisenberg joke, I was working for a guy who was an electronics whiz in physics in Iowa, and he said Heisenberg actually visited them at their house in Iowa, he said, and he sat in a chair in their living room, he said, but they were no longer certain which chair.